Hello students, welcome to EduCell. Today's session is all about to read the algorithm correctness. Here we will discuss why algorithm correctness is important and how many types of correctness of algorithms are there and what are the methods are getting used to correct an algorithm or to find correctness inside an algorithm. We will be discussing that one in the next slides. So here, correctness of an algorithm is important. As we discussed in the previous video, those who are new to this video, please watch the previous video. Here, correctness is important if the current output of your algorithm is equivalent to the expected output, then only you can say your algorithm is desired algorithm or correct algorithm. Like the same example I'll say, if you know you have written a code to find whether a number is even or not, in that time uh, if you're putting a number is 10, that time if that as per the expectations 10 is even. If your code is giving 10 is odd, so your current output which is odd is not equal to the expected output which is even. In that case, even is not equivalent to odd. That time what happens, you can say it is not meeting with the uh, expected output, so that's why it is not correct. If some part are getting matched, so you can say it is partially correct. Okay, if everything is getting matched, you can say totally correct. Suppose you can say you have given a answer, given an answer for a question which is totally correct, that so it's 2 marks that you got out of 2 is given by the teachers to you. Okay, that is totally correct. Sometimes what the students are doing, like to get zero point 0.5, sir at least give us zero point 0.5, zero point 0.5 means they know zero point 0.5 will be 1. Okay, but zero point 0.5 you are actually going for arguing with the faculty, sir please give us zero point 0.5, because you are partially correct. You're partially correct, you are not fully correct. So in that case what happened, like the partial correct is somehow you are meeting with the expected output. Suppose instead of getting suppose 1 2 3 4, like up to 10, suppose you would need to find, instead of getting up to 10, you are getting 1 2 3, like up to, again you are repeating with 2 1 2 1, like this. Suppose you are infinite loop, you can up to 3 it is running. Somehow you are matching with the expected one, but it is not totally correct. The partially correct answer we are actually not needing in algorithm. Is partially correct is not our target. The target is to get total correct. Why? Because we need a desired algorithm. That is why we should get a totally correct answer. So in the then why total correctness is needed, that you understood. Now total correct, if you want to find, what are the structures that you have to find. Before that, we should have to discuss one example through which you can easily understand what is happening now. So this is an algorithm we have written, or you can say it's a pseudocode, where array is given and length is given, where sum is decided as 0 because no need to keep the garbage value, that's why it is written as 0. So I is 0, it started from 0. Okay, so a length which is we defined, it has given there sum equal to sum plus arr, like each element will be added here. It's a you can say the code it is written is to add all the numbers inside the array indexes. Okay, we are adding the numbers or digits inside the array indexes. Okay, but one more thing you can remember here, while condition is correct, not an issue, but within that sum is equal to sum plus arr I. The I which is 0 is there, but there is no increment operator. If there is no increment or decrement at least operator, that time the while loop will not run. The while loop will be okay throughout. It's an infinite loop. Rather than going to stop it, we have infinite loop. Like it will check yes, then it will be printing some, then whether it will check yes, then it will be printing, because there is no such increment. Like how do we say it will stop? If the condition will be I is greater than equal to length, either in a different way also, if I is greater than length, okay, I is greater than ln or I is equal to ln, then only we can stop. So that is why I'm just writing it. If I is greater than equal to ln, then only we can stop. So to reach to that condition, we cannot do without any operator, which is increment operator, you can say. Okay, though increment operator we do not have, in that case it is considered as the stopping property. In one case, it could not be infinite loop if length is considered as 0, but length could not be 0. Okay, if you have written length is 0, that time it will stop, not an issue. One time it will run and it will stop. But if you have written 1 as length, means one index is there, in that case what happens, like it has to be 1 is always greater than 0. Okay, that time it will be, condition, like it gives you the result but not the correct result, because there are, suppose, uh, 4 indices, 0 1 2 3. So there are 4 indices. In that indexes, what you are doing, like 1 2 3 other values are being there. So sum will be, or you can say sum would be 1 plus 2 plus 3 plus 4. Okay, what would be considered as 10. Okay, sum should be 10, but instead of getting 10, so in this case, suppose you are writing length, I starting 0 and length is 4. In that case, it will be checking the condition, but the first only will give you the correct answer. Sum equal to sum plus arri. Arri means sum will be 0, then 1. So that will be your answer. Like we are going too far from the 10 also, like it is infinite loop, though we are going far from it. So we might get the correct answers as 10, but we are far from it. Okay, because it's infinite loop, sometimes though it is not stopping, so we are getting partially correct answers. It is wrong. Okay, it's not totally correct answers we are getting. So to stop it, we have to use this operator which we discussed now. So you can say total correct is equal to the mathematical model, you can say partial correct plus, it should be partially correct, plus stopping property or stop property, it has to be followed. Okay, if both are there, then only we can say we can expect total correct answer. It should be a partially correct answer, means infinite loop is there and stop property should be followed well, then only we can say it is totally correct. Okay, so here it is written, as you can see here, stops plus correct output is considered as totally correct answers or total correctness, you can say. Okay, now there are three, you can say, methods are getting used. One is counter example, another is induction, which is mathematical induction. Third one is loop invariant, and other approaches are there, but this is not inside the core man anywhere. But you can remember by cases enumerations also, by contradictions, by contrapositive. This could be done, but we should remember counter examples, induction method or mathematical inductions, or loop invariant. So loop invariant is, you can say, if the loop is not getting consistent. Okay, so if you are not getting the consistent result, definitely there will be a problem. That's why we are focusing on loop invariant. And the number of statements it is running, that we know, the statements will give you the correct output as one time it is running. But loop, there might be a problem in the conditions, so whether it is stopping or not, it has to be stopped with the correct answer. That's why loop will have some problem. That's why we are focused on loop invariant. First time how it is running, like this is your initial steps. Next, how many times it is running, like you are in a maintenance step. Once maintenance is okay, also you have to check whether it is stopping or not. There are three steps. First is initial steps, next is maintenance step, last is your end step, or you can say the stop step. You can have to check. If 3 will be true, then you can say loop is invariant, or loop invariant holds. Okay, loop invariant holds, you can say. If only one step is holding, only loop invariant, you cannot say every should or all the loop elements would be invariant here. It is not holding because only one is not enough. Suppose initial is okay, not an issue. Suppose for loop you are saying for I equal to 1 and I is less than 10, I plus plus. Here initial will be you have to check I value, you have initialized it. You have to check whether 1 is less than 10 or not. If it is done, you can enter into the statements written there. Once it is done, initial part is over. Like you have installed the AC. If you are having a problem like air condition, you need to install. Installation is done. Next, you are paying money for the maintenance. Maintenance will be from it will be running until the condition will hold. Okay, like you're paying the maintenance without initializing or without installing AC. You are not paying the money, like you are not paying the maintenance fee. That is how it is running. Okay, so first step is initialization, second step is a maintenance. You are checking it how much time, like up until 9 is greater than 10. Like up to this you can have expiry date, before the expiry date. Okay, up to that we can have the food, we can have to use the maintenance, everything would be maintained well. But if you have to check, if it is not working, then we are throwing the products. Clear? So where the I value, like it is 10, 10 is not equivalent to 10, which is you can say if I value which we said, if it is equal to 10 it will stop, and if I is greater than 10 then it will stop. This stop is end version of it or stop property of it, which is the third one, where you have to check the loop is invariant or not. Okay, so it's a though a loop is a problem, so that's why we are focusing that one. Next is counter example, which is said as indirect proof, and induction, which is mathematical induction, is direct proof. So counter example, everyone, when you are quarreling with a person, okay, with an example I'm telling you, whenever you are quarreling, okay, that time nobody in the earth is saying this is my fault. Nobody is accepting that the fault of themselves. That's why the quarreling will be the growth of the quarreling would be any more than that, more than the, you can say, super polynomial. Okay, it's a super polynomial. If nobody is understanding the fault, their own fault, everyone is alleging, no I'm not doing, you have done. So like this, a counter example is like this. So whenever have the problem is given, there you can take a random value, you have to fix it, you have to disprove or prove it. Basically we are going to disprove it, which is easy for us because we people are actually not maintaining, like not thinking no we are a culprit. We are always saying in front of us who is there, he is a culprit or she is the culprit. Like this is what a counter example is. So you can say to prove or disprove it. So x y within this ceiling function, whether it is equivalent to ceiling of x plus ceiling of y or not. To check that, so we have taken x value as half, like 1 by 2, y value is 1 by 2. You can check the LHS and RHS side of it. Okay, in LHS it is there x plus y, which is having ceiling function. You can say 1 by 2, which is the value of x, and 1 by 2, which is the value of y, with the ceiling function. That ceiling function will be picking the next value of it if there is a decimal. Here is no decimal, so the same value will be considered as 1 as a ceiling function here. And RHS side is like x with a ceiling plus y with a ceiling is there. You can say 1 by 2 with a ceiling plus again 1 by 2 with a ceiling is there, which is 1 plus 1 is 2. Like zero point 0.5, the ceiling will be the next round value or next whole number will be written. So that's why it is 2, where LHS is not equivalent to RHS. Here you are disproving it, okay, by taking any example. That's why it is said to be indirect proof. You are not doing it directly. You are taking any of this. Okay, so like this, every positive integer is sum of two squares of integers. It is written. You can take the example of 3 also. Here in the third example, it is written. So for all x and for all y, xy is greater than equal to uh, x, so that you can take any value of x. Here the value of x is -1, value of 3 is y is 3, so x into y is -3 because minus 1 into 3 is minus 3. So minus 3 is not always or equal to greater than equal to the x, okay, which is said to be minus 1. Though it is not equal, you have disproved it. This is how the counter example is working. Okay. Now, proving of mathematical inductions, maximum of you have done this in a intermediate level or might be 10th level. That time you have already seen. So a summation is given, like we have seen this mathematical model, which is this summation in indirect way. If you can ask me a mathematical way, you can say it's a for loop where I is starting from 1. Here it has there written I equal to 1. Okay. So I will be starting from 1. I will be ending with this one, so I will be less than n or equal to, you can say, though it is summation. Then the value it is running is, though it is one like adding of the thing, you can say I plus plus. It is the mathematical representation of a for loop. Basically, we are using. Okay. So and also though you can say it is running for n square time, the time complexity in that case, what you have to say, again one for loop, the same for loop you can say running for two times. If you say the time complexity of this summation is how much time, like if you're following this one, so you have to use another for loop for it where the same condition is running for two times. Yeah, the time complexity could be for this is n square, but it will be read by you the next videos, don't worry. Okay, so it's just an discussion that we have done. Next, you focus like the mathematical induction. The mathematical induction is needed to prove it directly whether it is following or not. So for that first case, you have to take the best solution, like from starting from a simple one. Like you can check with the one, the n value you have to take as one. Once you have taken with one, then you have to go for the proof. Okay, so this is how the first step is. Step one says, step one, less, or you can say smaller value will be taken as input. Okay, so here you can start with 1. If you want to take 5 also as n, so you can check that one whether 15 the side is equivalent to that one or not. Okay, so you have to check it, it is okay now. Okay, next for this mathematical induction, as we told, to prove that one we have checked it, one side and equal to we have written is 1, so it is there. And next we have to, in step 2, step 1 we have checked with a smaller value. Next in step 2 we assumed that it run for already run for n times, and we got a correct answer. Next we have to prove with n plus 1 time. Why? Because if the next step is true, then definitely the previous step could be true. So to say previous step is true, we are assuming, let us take it is okay. Next we have to prove for the plus 1 or the next step of the n, or might be anything which you have taken. So the here I kept for the left hand side and the right hand side as an example. So here we know the summation is all about to add the thing, you know? So we have just added it 1 2 3 up to n, it has to run, and here we kept as it is. Then here what exactly we have to do, by writing this n plus 1, okay, we just add to next step, because this is true for us. This is what true, that we said true if it is running for n plus 1 time. So what we have to do, we have to just run for 1 n plus 1 time, which is, you can say, instead of 1 you put n plus 1. Okay, here also you can put, instead of n you can put to n plus 1, because you are saying n is true. Okay, n is true, you are saying. Now you are proving n plus 1 will be true. So though you are proving n plus 1 is true, you have to put the n plus 1 in place of n. Okay, so here this is the answer. Next to to equate this, you are getting the answer as like 1 plus 1 minus 1 will be cut as 0. Then up to this you got the answer as, which is the proof that you said, like it is true, that's why you are writing it. So I kept it a bracket. Here you have written as the answer that you have already proven, okay, this is correct, and you kept as usual. And here also no need to do anything, so you keep the right hand side other way. Here when you are actually doing it, like you have to add it. Like whenever you are adding, the total will be looking like this. So I'm just writing it here. Okay, done. So which will be written like this. If you add this, only one like here two will be there under this, where you can write the answers like this. Okay, and then you have to take common of n plus 1. Once you have taken common, here LHS equivalent to RHS. Okay, though it happens, so you can say we have proven like the formula is getting proved for n plus 1. So though we proved it for n plus 1, so we can say n is also true. This is how the mathematical induction works. Okay. So mathematical induction is a direct proof. Without mathematics, we cannot say whether it is true or not. So in this way, we said the methods we are using in uh, correctness is mathematical induction, which is a direct proof, counter example, which is indirect proof, any values you are keeping, and third one is loop invariant, which you actually studied during the slides. And correctness are two types. One is total correctness, another is partial correctness. Partial correctness we don't want. For getting total correctness, is partial correctness plus top property. This is how our today's session is all about. I hope it is understood by you. If any problem, you can message below. Okay, and thank you for watching. Have a good day.